ഹലോ കേൾക്കാമോ? Hello, am I audible? Hello.
Hello, sir. Hi. It's audible, sir. Audible.
Audible. Very good. Okay.
Yeah. So we'll start by 10:30.
Fine.
Yeah.
Let me see where is the upload for the there is the upload share screen. Okay, it is there. Okay, fine.
Yeah, share screen, sir. Yes.
Okay.
Good morning.
Good morning, sir.
Good morning, very good morning. I could not switch on the camera. I said, no, okay, it's okay, I'm coming. So it's audible.
Yes, sir, you are audible.
Okay. Be ready. When Father Manager joins, we will start the meeting.
Okay, sir.
So only 4 are the participants. Or Sam? Rohit?
Sir, could you able to hear me?
Yeah. Am I audible?
Yes, sir, you are audible.
Sir,
So
you are
now,
audible.
so how many participants so far?
Sir, manager is here.
Okay.
John, sir.
Good morning.
Oh, good morning. Good morning.
Good morning.
Mr. Thomas sir is there, huh?
I am there.
Yeah, okay, sir. Then I think it's time to start. Okay, then. Are you ready, students?
Yes, sir. We're ready.
Yes,
So
sir.
I will start with a silent prayer, 1 minute prayer. Okay.
Yes, sir. So, good morning and welcome to the 59th National Metallurgists Day. We'll start with the silent prayer. Thank you, everyone. So, good morning and welcome to the 59th National Metallurgists Day celebrations. We are your hosts. I'm Sam and
I'm Alina. Over the last couple of weeks, we at the Metallurgical and Materials Engineering Department of Amal Jyothi College of Engineering have been organizing various events such as puzzle, quiz, and other events. And today we end up with this amazing webinar.
So thank you everybody who has come here. And first up, we have the welcome speech by our own, very own Dr. John Felix Kumar, our beloved HOD. He has been the cornerstone of our department for many years. He has been a great inspiration to each and every one of us in the department and in the college. Sir, if you would please.
Yeah. Good morning. As head of the Department of Metallurgical and Materials Engineering, Amal Jyothi College of Engineering, Kanjarappalli, I invite you all for the webinar as a part of a National Metallurgist's Day celebration. Amal Jyothi means a form of pure light. It stands for enlightenment to Holy Mary Immaculate, to whom the college is dedicated. We proudly note that today, 8th December, is the Immaculate Conception Day of Virgin Mary and the Foundation Day of College. For the past 2 decades, Amal Jyothi has been gloriously functioning. Is it audible?
Yeah.
Yeah.
Yes, sir.
Very well.
Yeah, okay. For the past 2 decades, Amal Jyothi has been gloriously functioning under the leadership of fathers of Catholic Diocese of Kanjarappalli. With pride and honor to announce that ours is the only institute in all over Kerala offering this unique branch of engineering. I take this great opportunity to welcome you all for this occasion today. First and foremost, I wholeheartedly invite our Reverend Father Manager, who is the guiding and driving force for all of us in this great campus. I welcome you, Father. Next, we invite Mr. Joseph, National Vice President, Indian Institute of Welding, for the presentation. We extend a warm welcome to him, sir. Next, I invite Mr. Thomas Tharian, former General Manager, Materials, LPSC, ISRO Trivandrum, who developed materials for Cryogenic Engine and other liquid engines, and also developed special steels for space application, engines used for Mangalyaan and Chandrayaan missions. Moreover, SR has published more than 125 papers in various reputed journals. We are more privileged to have you with us today. Finally, I invite my esteemed colleagues and my dear students. I welcome you one and all. Thank you.
Thank you, sir, for those welcome words.
Next up, I invite our beloved Reverend Father, Dr. Matthew Picard, for the presidential address. Reverend Picard is beloved by all students at Amal Jyothi. Under his leadership, Amal Jyothi College has become one of the prominent engineering college in Kerala.
Certainly.
Good morning to you all. Today's chief guest, Shri Thomas Tharian, former General Manager, Materials, Liquid Propulsion Systems Center, ISRO Trivandrum, who generously consented to give the webinar talk on materials for aerospace applications. Mr. Jos Philip, National Vice President, Indian Institute of Welding, who graciously agreed to give a few words of appreciation. Dr. John Felix Kumar, HOD, Department of Metallurgical and Materials Engineering, Amal Jyothi College of Engineering, the deans, HODs, faculties, and students and participants from different colleges and schools. Each year, 14th of November, which is the birthday of India's first Prime Minister, Pandit Jawaharlal Nehru, is a notable day in the calendar of the metallurgical industry of India. It signifies the National Metallurgists' Day. On this day, the National Metallurgists' Day Awards, instituted by the Ministry of Steel and Mines, Government of India in 1962, and presently under the aegis of the Ministry of Steel, Government of India, are presented to distinguished and meritorious professionals from metallurgy and materials science and engineering. The awards are nominated based on their immense contribution to the country's economic development in general and for outstanding contributions in the metallurgical fields, including operation, research, design, education, waste management, energy conservation, etc. The Department of Metallurgical and Materials Engineering, Amal Jyothi College of Engineering, Kanjirappalli, is organizing a one-day educational program for school UG students as a part of 59th National Metallurgist's Day celebrations. As like in previous years, the program includes JCJ Memorial Metallurgical Quiz Competition, technical and informal events, and the objective is to help students to get familiarized with the latest technologies in material development, which can take them to an international career. It will be highly beneficial for students who wish to pursue an engineering career, as well as those who are currently doing their graduation. Ever since the inception in 2012, the Department of Metallurgical and Materials Engineering has continued its glorious expedition, enlightening youth minds to explore the world of materials. Amal Jyothi is proud to be the first college in Kerala offering this unique stream of engineering. Here at Amal Jyothi, we are training the next generation of metallurgical and materials engineers to work with industry, entrepreneurs, and scientists. Together, we tackle the material of the future. I thank all the members of the Department of Metallurgical and Materials Engineering, Amal Jyothi, and appreciate their untiring efforts in organizing this event. I wish all the best for all the enthusiastic participants of the various programs and the winners of the competitions. Wishing you all a very productive session. I conclude. Thank you. Thank you.
Thank you, sir, for that incredible welcome to all of us. We're very grateful for having you here. The Indian Institute of Welding is one of the most prestigious professional institutes in India. It has been working towards the advancement of welding sciences and technology in India since 1966. It has spread its reach all over India to become a top-tier institute in India. We are honored to have the support and backup of such an institute in every event that we have done. I invite the prestigious Vice President of IIW India, Mr. Jose Philip, for the felicitation. Sir, please.
Thank you. A very good morning to you all. Yeah, I think I am audible to you.
Very well. Yeah, it's okay.
Okay.
Yes, sir.
The president of this meeting, Reverend Dr. Matthew Paykat, manager of the Amal Jyothi College of Engineering, head of the Metallurgy and Materials, Dr. John Felix Kumar. Today's seminar speaker, Mr. Dr. Thomas Tharian, former General Manager of Materials, LPSC ISRO Trivandrum. Dear professors, faculties, dean, principal, and dear students, I hope today is a very important day for Amal Jyothi, conducting this seminar on materials and metallurgy. where the only one college in the state, in the private sector, having a course on materials. In regard to welding, see, I represent the Indian Institute of Welding. The welding and the metallurgy and materials go in hand. And we are doing the promotion of welding wherever new materials, because since the government, the industry is progressing well and technology is developing very fast. In the industry, there are new materials and new metallurgy technology is also coming up. That is why I told, and all this unification of these materials or joining of materials, new type of new technology in the welding field also is expected to develop. So wherever materials and metallurgy is there, welding also is there. So that is the importance of today's program. And I'm very happy that Amal Jyothi College is encouraging metallurgical and materials professionals in your college. I am associated with Amal Jyothi College Engineering for the last 5 or 6 years through our institute, while I was the chairman of the IRW Kochi branch. I visited several times, taken classes and many associations, and also with the help of the management and Professor Laikat, principal, and Marin, we could establish a student chapter in the college. So these are the activities we are doing, especially for the college. In regard to the activities of IAW, I would like to say, basically our objective is promoting welding technology. Our headquarters is in Kolkata. This institute was established in the 1966, and we have a plethora of members, around 4,500 members from welding field is in our membership, and also about 300 corporates, as also in the industrial corporate members, including institutions. Every year, we used to conduct international exhibition and welding seminar, along with the national welding seminar, and also where professionals in the welding field used to assemble and presenting papers, discussion about the advancement happening in the world in the field of welding. Also, we used to conduct national weld meet, national level. It will be a one-day program. National welding seminar will be a 3 days program. If it is connected with the exhibition, it will be 5 days program. Last year, the program was conducted in Mumbai. And regard to our branch activities concerned, IRW Cochin branch established in 1978. And we are conducting plethora of programs, seminars, workshops for the benefit of the welding professionals and the students. Our prestigious program is a CSR initiative project of Cochin Shipyard, giving training for 60 youths who was covered age of 18 and just passed the 8th class and should be BPL category, below poverty line category. We are giving them 5 months training in welding. The total welding time is 600 hours. Out of that, 540 hours is practical and only 60 hours is theory. So people are benefited with this. especially youth, immediately after 5 months course, they are getting placement from various companies, industries on their experience, because they are getting a continuous welding practical training of welding. It is being conducted at Don Bosco, ITI, Vadodala. So far, we have trained about 180 youths for the last 5 years. The interesting part, after passing out this course and join with a company, either Gulf or Middle East or local, this BPL family is transformed to APL family, because with one welder working is working in a family, he gets a sizable amount of salary, so that the societal upliftment is happening with only with the course. Second is in regard to for the benefit and exposure to get in the welding for the engineers. We are conducting a national young engineers competition, which is going to happen in the month of January. We are inviting papers. Normally about 11-12 teams across the nation are participating. They are to present a new project conducted by themselves as a team. The first prize will be 50,000 rupees, and second runner-up will be getting 25,000, and third place will be 10,000 rupees. For the last 6 years, we are conducting. This is also for the benefit of the students and youngsters. The maximum age limit is 35 years. This is for the benefit of the youths and young professionals. And we are conducting normally workshops, training programs, technical visits, and other like programs continuously for the benefit of the people or professionals in the welding. And short-time courses also we are conducting in the welding field. That is around about our institute. Rather than this, I would like to tell about the prospect of welding in our country. See, welding is related, or steel or materials. Consumption will be through the joining of materials, because joining of materials easiest method and developed method is welding. So steel consumption should be increased by applying the welding technology. Today, India's steel production is second in the world. First is China. China is the largest producer, about 760 million tons they are producing every year. Whereas India is 110 million ton, US is around 108, Japan is 101, like that goes. Now our government of India has planned to increase the production of steel to 300 million by 2030. The production plan, everything is going on to catch up that production of 300. That means 3 times will be the steel production. So you can just imagine is the prospect or area of opportunities are going to be developed in the year by since maybe 2025 to 2030. The requirement of even the professional engineers for the last to the next 7 years or 8 years will be around 250,000. So there is ample opportunities for engineers in the field of welding. In the operating level, welders also will be 5 times of that figure. And when the industry grows, definitely welding technology also should grow. That is what I told, that new materials has to come. Because in India, majority of the production is carbon steel materials. Now, production also for stainless steel, and especially we have to go for nail steel and duplex stained steel, where withstand the atmospheric rusting. These are the new materials. So further, many materials has to come in our market, in Indian market. So research and development in metallurgy area is required. That is another area of getting opportunity for our professionals in the metallurgy and materials field. For example, the substitution of import materials. Many special materials still India is depending on importing from other countries, developed countries. We have to develop those special materials in our country on domestic technology. For example, where we want to construct the first aircraft carrier in India, that is being built in Kochi shipyard. Many thousands of tons of steels are required, where special metallurgical importance are required. When we went for global tender, the countries, developed countries, have quoted very high price for that material, because they know India don't have that capacity to make that steel. But immediately, government of India has sense that they are exploiting us in the special materials. Government decided to go for manufacturing of that special materials in India, and our Steel Authority of India developed that materials. Actually, that material is used for first aircraft carrier being made in India. Like that, lot of import substitutions are required. New material has to be developed. No material development means new welding technology for weld, that also is required. So you could imagine the prosperity and growth in the development of welding technology in our country. Another statistic says the average welding steel consumption per capita all over the world is around 240 kg per person. In the case of US, it is 450 kg. In China alone, it is around 380 kg per person. But look at India, average per person consumption is only 56 kg. There also, our steel consumption is very, very low. 56 to 250, world average, so 5 times is required. Our steel consumption is very low. So we have to increase the steel consumption. As I told you, by 2030, 300 million is going, the production is going to increase. That much steel we have to consume here, especially in the field of infrastructure facilities, industries, manufacturing sector, because huge requirements are there for our domestic consume. We should, instead of now, India is going for concrete roads and concrete bridges. Instead of that, we have to use steel bridges for construction of roads and for the bridges. Especially building construction, also the steel consumption is very less. That is the characteristic of India. But whereas US and all, they use steel much in the building construction, because that is faster, that is economical, and we also should. We are still in the obsolete technology, going for the concrete construction, where quality is also affected. You could see many failures in the concrete construction. And very high structure and highly irregular bridges are made of steels. So these are the prospective areas coming in the field of welding. And I'm very happy that such a seminar is going to benefit our students, those who are eager to learn more in material and metallurgy science. And the college is also putting a lot of effort for supporting the students. We also have plans for the benefit of the students for short-term programs about the welding technology. It will be introduced soon, especially through student chapters. We are going to take those programs to the students so that by the time they leave the college after studies, they will get some idea about the welding and building technology. And also the industrial visit and study tour in welding also we can arrange with the reputable institute in and around Kochi or anywhere, because if they see and they interact with the industry only, the students will get more interest in the welding fields. So that also we can arrange. And also I'm very happy that Professor Marin John is taking a lot of interest in nurturing the student chapter. I request those who are interested in the welding field to join with the student chapter, and we can do a lot of things for the benefit of the students that may lead them to find out an opportunity after their studies. And also those who are interested to concentrate on R&D, where we are already opened R&D center in Baroda with huge infrastructure facilities that also can be used by the researchers. And I request we should have more interaction. The institute and IIW, the college and institute, have more vibrant relations for the development of building technology for the benefit of the professional science students working in the field. I'm very happy in taking initiative by Amal Jyothi College in the interest of the students for the in associating with IIW. We can have more programs hereafter. I thank the organizers for inviting me for this program of inauguration of the schedule for NMD, and I wish all the success for conduction of this meeting, and especially you are going to attend a seminar also after this meeting. So thank you, wish you all the best. Thank you.
Thank you, Mr. Joseph Philip, for all of your wonderful instructions and your wonderful speech about welding and IIW. Thank you for all the encouragement that you have given us. Next up, we have the inaugural address by Shri Thomas Tharian. Shri Thomas Tharian had an illustrious career with various achievements to his name, such as he has been the former general manager of the LSPC of the Indian Space Research Organization, ISRO. Shri Thomas Tharian graduated with a BE Metallurgical Engineering from MNIT Jaipur. He then worked in Communico Binayaki Zinc Alway for 1 year. He then graduated as MTech from IIT Kanpur, joined ISRO in 1988. He has worked in several projects, such as developing materials for Cryogenic Engine and other liquid engines, developed special steels for space application. He has developed engines used for Mangalyaan and Chandrayaan missions. He has published more than 125 papers in various material journals. He finally retired from service in July 2021 after 33 years service in ISRO. We are honored and respected to have him here to present this webinar today. Sir, we invite you to give the inaugural address. So
Yeah.
please.
Thank you. Thank you very much. Good morning to my dear students, teachers, and faculty members of AJC. And it is a pleasure to talk in front of my dear students and teachers of AJC on the occasion of 59th National Metallurgist Day celebration. As you know, metallurgy is the oldest engineering topic, which even started beyond 3000 BC. Since the 1960s, the term has come to label the general branch of engineering concerned with material, and it is the material science and engineering. This label is inaccurate in that field since it is true blend of fundamental scientific studies and practical engineering, because to develop a material, we need both fundamental scientific studies as well as we convert that into a practical product. Material find application in all parts of our life, that has been household, transportation, construction, defense, power sector, and even aerospace areas. They also play a very important role in the emerging programs of advanced technology sectors like space and defense. For space sector, reusability, human space travel, re-entry vehicles are some of the focus areas at present, because it is very all over the world. Actually, we see when I joined ISRO, hardly there were only NASA, USA, then of course Russians and China were the key players. Now I can see every continent we have in lot of people are actually a lot of countries supporting investing in space sector. So please think this is a very, very important sector compared to any other sector like nuclear or power sector or anything similar to that. Any compromise on the space sector, the robustness of material that protects the space capsule can be a catastrophic event, because it's very sensitive. For a human space, actually, we have to ensure the quality of the material used, double or even 3 times. So it is that material, production of that material is going to be a costly affair. Most interestingly, 40% of the cost of the typical launch vehicle goes to the materials. So when you make a launch vehicle or a rocket or a space satellite launch vehicle, 40% goes to the material solely, and balance 25 to 30% goes to the fabrication involving metallurgical operations like forming, welding, bracing, heat treatment, etc. And the remaining 30% really goes to the propellants, technology, labor, tracking, salaries, etc., and everything else. And all over the world, people working in the space area, space sector, they are actually trying to make new materials for making a lighter, stronger, and faster and safer launch vehicles of the future. In India, the indigenization is one of the targets set forth by many organizations. Material scientists work real hard to achieve this, because one of our problems is actually many of the elements required for making an alloy actually is not available. We have to depend upon the foreign countries. It is that actually every country will have the basic ore, like nickel. We don't have. We are importing nickel. Like that, I can show you many examples. This reduce. So in the so we have to import the alloy elements and they make the alloy within the country. So this reduces the dependency of many important materials from other countries. I'm proud to say that actually in ISRO, actually for especially liquid engines, we use more than 120 types of alloys actually. In fact, almost 90% of alloys have been indigenized, except for some brace alloys and some filler wires. That also we have taken steps to indigenize, so that actually the cost towards the Atmanirbhar Bharat has been driving our industries for some time. Material scientists play an important role in the country's economic development. Institutions of eminence in India include Defense Metallurgical Laboratory, Nuclear Fuel Complex, Baba Atomic Research Center, ISRO, and NML, and NFTDC, NALCO, SAIL, Tata Steel. There are, I can cite a lot of industries actually. They are growing. When I joined ISRO, actually hardly only one industry was there. Midani was the only steel maker who could make a steel doubly refined. Doubly refined is actually normally whatever material steels we are getting in the open market actually is single time melted. Whatever we are using, or defense sector or anybody, any special steel people are using, there have been doubly melted. I mean, that facility was not available only in Midani when I joined. Today we have encouraged other industries, and now at least I'm having more than 5 or 6 industries in India who can make this material, special materials with the double melting like vacuum arc refining or electrolytic refining. And Indian Institute of Metals, IM, is a reputed materials body devoted to the promotion and advancement in the study, practice, and research of material science and technology. They bring all these people, I mean, all the researchers and academicians together, and they make a consortium and kind of thing, which will make the development of a material much easier as we think. And IM also runs promotional events where opportunities for elaborate discussions and exchange of ideas among all scientists of, and engineers of our country. It even provides travel grants to encourage giving presentations and international conferences. There is a massive opportunity for students and researchers to contribute in metallurgy and material science and make India a global technology powerhouse. New advances in additive manufacturing, nanotechnology, multifunctional aerospace, joining techniques are all encouraging science for our students. I don't think that actually just like computer science, you won't get any chances in metallurgy. Metallurgy have got more chances than computer science. I can guarantee that. The advanced directions, materials, technology, and processing of metallic materials are stipulated, and increasing technical requirements to the materials are in connection with the modern engineering. Modern engineering, in fact, helps. In fact, the automation of many metal things are happening around the country and the world. So you don't need for doing heavy, like a heavy rolling, forging, and you don't need a physical manpower. It can be done by a robot. Then in this connection, it is possible to select the following base tendencies of the development of alloys. First is generation of new materials with predetermined physical and mechanical properties. Second is the development of new source saving process of treatment of both traditional and new materials, and the application of new techniques of heating and cooling at heat treatment and metalworking operations. In this connection, I will give more information in my presentation on aerospace materials. How many of you know on which date NMD or National Metallurgist Day is celebrated? It is 14th November, Pandit Jawaharlal Nehru's birthday. He envisioned the industries as the temples of modern India to lead the industrial revolution out of realization that manufacturing sector and modern and material processing were the vital for countries' economic growth. In fact, actually, all first IITs have been set up by him. Whenever I go to IIT Kharagpur, I see the foundation stone laid by Pandit Jawaharlal Nehru. I'm happy to inaugurate this function and webinar. I wish the participants and organizers a great success. I'm sure this event will provide a food for thought in the right direction for all participants to achieve their aim. I want to thank the organizers for this event, for webinar inauguration and presentation. Thank you very much.
Thank you, sir. Now we invite you to inaugurate the National Metallurgist's Day. Thank you, sir. There is an announcement. After the webinar, the winners of the events conducted over the last few weeks will be announced. Next up, we would like to invite the Secretary of Syndicate Metallurgical Engineers, Said Hudayfa, to give the vote of thanks. So please.
Thank you, Alina. I'm grateful to extend my vote of thanks to the dignitaries present. So I'm Said Hudayfa, the Secretary of SME, and extending my vote of thanks to everybody present here. Firstly, I'd like to start with Shri Tharian, sir, a renowned scientist from ISRO. I'm very thankful for him to bestow his time upon us upon a very busy schedule. I'm certain that every person, not just the participant, will draw inspiration and motivation from the seminar and also understand the importance of metallurgy and material sciences in various fields. And then I'd like to thank Mr. Jose Philip for making time again from his busy schedule. Also, the National Vice President for IIW, who has been helping us with the Kochi chapter all along. And despite of this COVID situation, through the thick and thin, he's been supporting us all along, who has been providing us an extended support. The event wouldn't be possible without you, sir. Thank you, sir. Then we have our Reverend Father, Dr. Matthew Picard, and our institution is greatly thankful for him because he continuously supports us in every event possible and making time for us in this Advent occasion. We are really glad you're present here. Thank you, Reverend Father Dr. Matthew Picard. Then I would like to thank our head of the department, Dr. John Felix Kumar, who has been like a pillar to our department for always keeping in check for the event, always looking out for a back. He's been relentlessly working with us all along. Then I would like to thank our faculty members who don't get the spotlight much enough, but they work day and night, and they're always like supporting us and help this event go through all difficulties. Thank you for always being there. I would like to thank each and every faculty which is present over here. Then I would like to thank my fellow SME members, like they all the work, like in the dark. I'm really thrilled and I was really hopeful for the event. He just used every day and he was like, we have to make this event really successful. And we have Siddharth, also the backbone, who made these presentations, these posters and etc. I thank you everybody for your effort. Then I would like to thank all the participants which are listening to everything with utmost curiosity and open minds. And I would like to extend my thanks to you too. And in the end, I would like to thank Father Ruben from the MCA department and Church Saint Sebastian for setting up this Zoom platform facility for us to make it easier and a good going smooth webinar. And I'm real thankful. And I also humbly apologize if I missed anyone at this point. But I would like to thank for making this event really successful. And I hope you'll come here again, and I'll get to meet you all again. And next time will be bigger, greater, and better. Thank you.
Thank you, Shahid, for that incredible vote of thanks. Finally, we have arrived at the event that we are all here for. I am elated to invite Mr. Shri Thomas Tharian for the talk on materials for aerospace applications. Sir, please.
Yeah, let me share the screen. Is it visible?
Yes, sir. It's visible, sir.
Very good. Okay. So, good morning to all. Well, I've been working last 33 years in this material development and rocket engine fabrication. Okay. I have two requests. First of all, I have my presentation will run up maybe an hour maximum. Plus, I expect a lot of questions. That is, I mean, I want more questions. Then only I'll improve myself. Plus, you will also gain some whatever I knowledge. I want to share it because now since I'm out of ISRO, I want I have a good passion to materials. I want whatever knowledge I'm having, I have shared to you and my younger students, friends. So this is actually very, very important. Okay, I mean, sharing the knowledge because you should carry over. I mean, take over things the baton from me. Thank you. Good. So my title will be something like this: why materials? Why at all we are talking so much about materials? Okay, and every day if you see There are a lot of forums available where people are discussing about materials and metallurgy. Materials for launch vehicles, because I specialize. So today's I'll be talking mostly about metallic materials which is used for launch vehicles. Maybe a bit all topic, but my youngest friends, my students may not, may it will be an opening for them actually. Then aerospace material requirements, basic characteristics of materials, why, what are the special things which require for aerospace materials. Then some of the strengthening mechanisms you are using. Then we are using cryogenics as well as high temperature in our rocket engine. So what are the special materials required? Then some of the environmental issues, very, very interesting. It has been, I mean, very little study has been gone into the environmental issues of the rocket engine, because only NASA has done some studies, and most of the studies, I mean, they are publishing it, but very late, because at least 10-15 years old thing only they are publishing it again. By the time they are got into another area, so we don't have much data on this, and nobody is investing in that. That is another sad thing. Then finally, I'll come to some of the materials I have developed, which has got I got some passion for the material. I mean, that materials. I developed a lot of materials, but these are some special things that I developed. Finally, I'll conclude. Thank you. Then, materials for space applications work in a wide range of environments. Each gram of the structural with respect to the payload is very important. Every time we try to modify the upper stage. I mean, rocket actually we have a ground. I mean, lower stage and upper stage. Upper stage will carry the satellite. Because there actually we will do a lot of research to bring down the weight so that actually we can increase the payload. And another interesting thing is actually in a rocket engine, the most interesting thing is the same material used will be exposed to propellants, sometimes extremely low temperature as low as liquid hydrogen temperature, that is -250 degrees centigrade or 20 K, or high temperature as, I mean, the same material will be exposed during the operation, it goes to temperature even more than 1000 degrees centigrade. So, I mean, the material has to work both conditions, either low temperature or very high temperature. Then the material decides the cost of placing the payload to the orbit. For expendable launch vehicle, the cost of placing 1 kg of payload in geotransfer orbit, it's about $30,000. So 1 kg, if I additionally put, I can save $30,000. Then for reusable launch vehicle, this figure is proposed to be something like $1,000. Earlier, I was telling in my others, I was telling about the cost breakup in a launch vehicle. Hardware is actually nothing but the materials plus the fabrication. Fabrication, actually, we don't have anything consumable. In the sense, actually, we have all fixtures, I mean, machinery is all actually permanently available. Only consumables we have actually material, fillerware, brace foil, etc. So that means actually almost 40 to more than 40% of the total cost belongs to material, and 27 belongs to, 27 to 30% belongs to your fabrication. That is in the form of salaries, utility of the machinery, etc. And rest you can see that actually mission engineering, launch campaign, propellants and fluids, mission support, insurance, project management, all salaries. So everything will come into that actually. So what I want to say is that material and fabrication constitute the most important part of a launch vehicle. So in order to bring down, because every country is involved in the launch vehicle program, they are actually trying to bring down the cost. So bringing down the cost of the rest of the thing is not important. Bringing down the cost can be made only by the hardware, hardware or the fabrication of materials. So imagine actually now, if you see SpaceX launch vehicle, Merlin engine, so it's a cluster of Merlin engine that he's actually putting in the Falcon engine. So it is actually, they have developed a new technology for fabrication, because of which actually they can make an engine within no time. This is another important thing about the payload ratio. For PSLV and GSLV and Mark III, see, every 150 kg of the strap-on is actually the ground lower part of the rocket. Every 150 kg, I'll say 1 kg of payload. So in the first stage, it will be 66:1, and the second stage is 10:1, and third stage is actually 3:1, and the fourth stage, the upper stage is actually 1:1. So what I mean to say is actually upper stage, whatever material we use actually is very sensitive to payload because it directly influences the payload weight which you are going to put in geotransfer orbit actually, or some SSTO. In GSLV, the same ratio is actually goes to 43:1. So first stage is 31:1, and second is 7:1. So 1:1. And Mark 3, it is our Bahubali of all launch vehicle, ISRO's launch vehicle is 25:1. First stage is 8:1. It's a liquid engine, and second stage it is 1:1. So very, very important. So selection of material, we cannot use just any material for launch vehicle application because of ultimate our idea is actually to place an satellite in the GTO. So we have earlier the same thing I was telling actually. International market is about $30,000 per kg. In India, GSLV is it is a very old figure. Every year actually this figure, this price, the cost will come down. With respect to our resource, this one. And GSLV market is actually $10,000 per kg. So it's coming down, and reusable launch vehicle, of course, it will be much less because we are going to use it again. Then this is our three launch vehicles which we are using ISRO. One is PSLV. That we mostly it is a 4-stage vehicle. We have a solid at the bottom, and second stage is a liquid. Again, third is again solid. Fourth one again is a liquid. And I worked in both the VSSC as well as LPC, and I got good knowledge about all these materials which used in PSLV and GSLV and Mark 3. And in the GSLV, we have it uses the cryogenic stage. Because of that, actually, it can take to 2,200 kg to GTO, and I'll show you why cryogenics is important actually for taking more payload. And GSLV Mark 3 is actually 2-stage vehicle to GTO, and it can take to 4,000 GTO. We have 2 solid strap-ons, that is two solid strap-ons here, and 1 liquid stage and a cryogenic stage. Now we are actually trying to develop a semi-cryogenic stage which uses actually liquid oxygen and kerosene. Once that is developed, actually this 4,000 will become suddenly to 6,000. That means 2-ton payload straight away again. So that we are keenly developing. I think within 1 or 2 years it will be ready. So even we can take up to 6-ton payload to GTO. Then this is the major materials used in PSLV, GSLV, and PSLV, and we have a upper stage. We use the lightest magnesium alloy electronic housing, heat shield aluminum alloys, titanium alloy tanks are used. Then we have important materials I'll highlight. Aluminum tank gauges are actually used for carrying the liquid propellants. There is a cobalt alloy system used for liquid engine, which is actually with a temperature is coming as high as about 1100 degrees centigrade. Then motor case is actually made out of M250 marine steel. That is our workhorse material. When we have strap-on material, which is an XSLA steel containing 0.15% carbon. Then yeah, these are the important things about PSLV materials. Then we have GSLV, same thing. Only difference is actually we have a cryogenic tanks here. Both are made out of aluminum and for storing liquid oxygen as well as liquid hydrogen. Then we have a cryogenic engine which contains copper and special steels for cryogenic application. Then similarly the case of PSLV, we have a liquid engine where we use cobalt alloy for the thrust chamber. Aluminum, instead of solid, here we have a liquid engine strap-ons. So there we are using aluminum alloy 2219, that is aluminum copper alloy as the tank gauge material. Again, engine will be made out of same cobalt alloy. Then marine steel booster is there. Then comes our Mark 3, GSLV Mark 3, where this 2-stage engine, we have 2 marine steel strap-ons will be there, S200, and one L100 aluminum alloy tank is there. There again cobalt alloy is used, and this is a cryogenic stage where actually we are using liquid hydrogen and liquid oxygen, and it gives about nearly 20 ton thrust. And here satellite will be placed. So, as I mentioned earlier, that why we are so much bothered about the cryogenic propellants and stages actually. It is actually what we need is actually high propulsion energy per unit mass. LOX, that is liquid oxygen, liquid hydrogen combination, gives the highest combustion temperature. It gives about 3,500 K and the lowest molecular weight of combustion products. Am I audible? I'm sorry. Am I audible?
Yes, sir. You're audible.
Okay. Then we have a new term. Actually, they normally in only on rocket engine people only use this term known as specific impulse. That is actually combustion temperature divided by molecular weight of combustion products under root. So the specific impulse of cryopropulsion yield actually 445 to 456. Highest performance is essential to. So this is, I mean, in other ways actually, it is the efficiency of the fuel oxidizer system to give 1 kg of thrust. 1 kg of fuel, propellant fuel system gives 1 kg of thrust, and it is a duration. That means actually it's the duration through which 1 kg of fuel combination gives 1 kg of thrust. So cryogenic gives the maximum duration for giving this thrust actually. So that means it can take more payload and it can travel more. So here are some of the propellant combination and the specific impulse. Like we have N2O for nitrogen tetroxide, and methyl hydrazine, unsymmetric dimethyl hydrazine gives 295, and these are all actually used in liquid engines. And we have mixed oxides of nitrogen, that's MON3, and then monomethyl hydrazine gives about 305. This only we are using in the satellite to take the geostationary orbit as well as the orbital control. This fuel only we are using. And then we have the LOX. These the 1, 2, 3. All the three we are using in the ISRO's program. In fact, outside NASA, Russians, and all actually they are using all the things actually. We have LOX crescent actually we are developing, which is known as a semi-cryogenic engine, which gives about 335, and LOX methane is giving is about 350 to 360. That is the new rafter engine which SpaceX is actually. Hello, yeah, tell me anything else. Can I continue?
Yeah, you may continue, sir.
Okay. LOX methane is giving 350 to 360. Why I'm talking all this actually? For the, I cannot use the same material used for the this two fuel combination we call as actually earth storable. That means it can be stored in earth. So that we call actually earth storable engines or fuels and oxidizer. Whatever I used here, I cannot use it for this application. So the material which I use using for LOX crescent, and I cannot, majority of I can use, but some special areas actually I have to use for different material. And LOX LH2 is totally different. So everywhere actually I have to use different material, and that makes the LPSC or materials or liquid propulsion materials where I worked last 10 years. We have using more than 120 alloys, including brace foils, filler wire, etc. Basically, the wrought alloys itself is actually more than 90 numbers, and they have been making all the alloys except 1 or 2 actually. I think we are completely indigenized through with the help of our industry partners like Midani, Starwire, and Kalyani Carbon at Pune. So what I mean to say, every system has got its own specialty. So that today's topic I'll be covering more, especially that, and how we are arranging the development of this material as well. So one of the problems with the cryogenic engine is that actually this is the biggest cryogenic stager ever made by NASA. I mean, that is Space Shuttle main engine. It is actually about 47 meter long and 8.4 meter diameter. Whatever we are making aluminum, this is made out of aluminum alloy. Actually, earlier it was 220, and then they switched over to aluminum lithium tank. So whatever the biggest tank which we are making at just over 4 meter diameter. So you can I mean, it's double of that. So aluminum and problem is actually after making the shell, we cannot do any heat treatment. So that means the weldability, I mean the weld efficiency is very, very poor. I mean it's hardly even just 50 to 55%. So what NASA has done, or I mean, outside what people are doing, ISRO also now made successfully. We are also launching, or not with aluminum lithium alloy. What they are doing it actually, they are doing friction stir welding to make this complete tank, both surseam as well as long seam welds. So it has been successfully made. Even ISRO also in PSLV and most of our tanks actually we have successfully made out of 221A. But NASA has actually used for the last flights of the space shuttle, they used aluminum lithium alloy, where actually, which we'll discuss in my presentation, which has got a much superior payload, gain actually. So they switched out to that, and they got that. So welding such huge thing is why I'm telling all this actually. Cryogenic tank, because hydrogen is actually lightweight, we have to make tanks as big as like this actually. So that's why actually SpaceX, they are not using cryogenic tanks, they are using only LOX kerosene or LOX methane, which doesn't need such big tanks actually. Even though there is a loss in what you call specific gimbals, they are managing with that. They make a lot of more engines instead of making one cryogenic engine. So that is the newer approach. Now we'll come to the aerospace material requirements. Till today, you can see all this. Till today, I don't have a single alloy which meets all these requirements. Okay, one alloy which is very close or very, almost 60% meeting is actually our workhorse material called maraging steel, which my ex-bosses in VSSC, Sri Kumar sir, Dr. Sinha are all actually, they are the developers of this alloy. And I'm proud of them because that successfully indigenous material and then this flight. So we have a high strength density ratio, specific strength, that's very important in order to give the maximum payload gain. Then we have high elastic modulus to density ratio, specific modulus. Then we have adequate fracture resistance. Everything margin still giving, but except for K1 SEC. The K1 SEC is nothing but fracture toughness in stress corrosion conditions. Actually, stress corrosion resistance of fracture margin steel is very, very poor. Then easy fabricability and easily weldable. Good, that is one very, very important, because I can make a lot of alloys. If it cannot be fabrication is difficult and it's not weldable, it's a problem. Simple heat treatment. Compatibility with the propellants, that is very important, and for fluids that I was discussing earlier. Then should meet the functional requirements, easy availability and reasonable cost. Because one alloy is still hurting me actually is that actually even I couldn't do any justice to that. One alloy which you are using in our satellite as well as in our PS4 is actually one columbium alloy, which we cannot make in India because only 2 manufacturers are available outside that, they are in USA, and this is very costly. That actually we tried because the alloying elements are not available, especially one alloying element called hafnium. And effective quality control is very important, because imagine for a human space mission we are taking people in our launch vehicle, then actually it is quality control is very, very important. Then for cryogenic application, ductile to brittle transition is very, very important. Material with no DBT only can be used, and the high temperature we need very high strength. So these are the some of the requirements for aerospace materials. But even engine to engine or system to system actually change. Then we have 2 categories. One is non-pressurized and pressurized. Non-pressurized means actually interstage, payload fairings, and pressurized means actually we have motor cases, tank gauges, gas bottles, etc. It will fall in that. Aluminum alloys and composites are normally use this in the structural application here actually. And aerodynamic shaping and housing auxiliary systems are some of the important characteristics of this system. And marine steel, titanium alloys, and aluminum alloys and copper alloys are the motor cases thing. They are mostly reaction vessels and storing propellants and pressures. Then how to make a good material? We have these are all interlinked. We have processing, structure, and properties and performance. So once you process, the structure will come, and structure will give properties, and it will be both will have mechanical properties will check, physical properties sometimes, and we have crystal structure and phases and microstructure are actually some of the outcome of this. Performance is finally it will guarantee. Then we have, when you make a manufacture a component, actually we have design, then design will give the material, we will make the material, and the process to make the component. If any failure is there, this will go back to the design and the material. So it is a concept loop. Then I'll come to some of basic metallurgy. I mean, this is most of the things you learned in your classes actually. So I just want to inform that all metals are actually joined by something called metallic bonding, and it is because this is important. Why I'm talking exactly why? That's why metals and alloys we are using it. High thermal and electrical conductivity, and it's got it's a cloud of electrons which fills the space between metals ions and glues the ions together to Coulombic attraction and between the electron gas and deposit metal ions. Metals are soluble in liquid state and have a restricted solubility in solid state. So this is the principle of our heat treatment actually. And these features, solubility is the basis of various alloys and intermetallic development. Then we have, this is also you have studied mostly, but I just want to refresh it, because for every application, this crystal structure, selection of material with respect to crystal structure is very, very important. And in general, I'll tell you, in FCC materials can be used low temperature as well as high temperature, and ambient temperature also, because ambient temperature, the problem with FCC materials, especially take the case of steel, we have all austenitic stains are actually FCC, and they can be used in all temperatures, high temperature, ambient temperature, as well as, I mean, of course, nickel alloys falls in FCC, so they can in low temperature also. But normally ambient temperature they are not used actually, because normally they are highly alloyed, so it will be costly. So they don't use they are not very much preferential for the ambient temperature application, but they are needed for high temperature application as well as low temperature application. Then comes BCC, that is our normal steels, which is actually normally used for only ambient temperature application. But they can also, they can be easily welded. But usage of this material is actually not advisable for low temperature as well as high temperature, because at low temperature they become brittle, and high temperature they become too much plastic. They don't offer any strength. And hexagonal close pack comes in between. In fact, actually only one alloy actually more prominent, that is titanium alloys, especially because they got an additional slip plane, because of which actually it is useful. Useful for any application. They can be used to some cryogenic temperatures up to 20 K. Only one alloy, titanium and titanium 2.15 can be used up to 20 K. And 77 K we have a lot of materials available. And high temperature also maximum 500, 600 degrees centigrade, not more than that. But titanium aluminate can be used for to 700, 750 degrees centigrade. But titanium is an important aerospace material because of its density. It's half of steel actually. That's why it's very, very important. So then there is a question actually, what are the strengthening mechanisms? All steel material actually strengthening mechanism is very, very important. The upper limit of the strengthening is actually limited by toughness. I can give an example that actually I have used both maraging steel as well as a material called bearing steel, the 440C, that contains about 1% carbon. Both has got nearly 1800 to 2000 MPa strength. Okay. The problem with marine steel is, problem with the 440 is actually it's highly brittle, and marine steel is actually ductile. Marine steel offers a fracture toughness of nearly 90 MPa/meter, whereas 440C gives fracture toughness of nearly 10 MPa/meter. That means actually it is brittle. We cannot use 440C in a tensile application. It can be used only in a compressive application. But it's an excellent wear resistant material. It can be used in the bearing races, knives, etc. But never, it cannot be used for a tensile application where marine steel is used. So that's what I'm telling. Strength is not enough. Then the upper limit of the strengthening is actually limited by toughness requirement. So we have an equation actually, K is equal to Y sigma by 4 pi A. As you can see, A is the crack size, half crack size, and K1C is equal to this. So based on this, actually, we can find out the available, in presence of a crack, what is the available strength of this material using the fracture toughness value. K1C is also a material property. The strengthening mechanisms are actually solid solution strengthening. That means actually you can add alloying elements to increase the strength. grain size. Do a heavy working, wet working to get a grain size, and by Hall patch equation, actually you can get a good strengthening. Normally, this is very useful in the austenitic stainless steel, where fine grains is very good strength. Second phase particles like precipitation or added particles, that is actually normally all age hardenable alloys. Actually, we have this dislocation. Dislocation is nothing but your work hardening, which introduces, that's a cold work material. It is highly dislocated material. Ordering is actually, it happens in superalloys, where actually precipitates are actually ordered structure you will get. Then we do a lot of testing actually to understand how a material deform, elongate, compress, twist, or break down as applied break as a function of applied load, time, temperature. All these are very, very important to select a material for aerospace. So first we have to see what are the testing we have to perform, so that actually we get the so you can select the material. Then we have tension, compression, shear. From there actually a yield strength, tensile strength, ductility, toughness, fracture toughness, and these are some of the things we may measure. And of course, this is done both basically for pad material as well as the weld coupon or brace joint. Wherever it is actually it's done before the actual induce, we will be doing the testing to evaluate the mechanical properties of the material. Then this is a tension test. Actually, various stages. We have necking. After the ultimate load, actually we have necking. Then finally material fails. Okay. Tensile strength, normally maximum when we have material up to 2000 MB also available. For structural application, yield stress is usually a more important property than tensile strength, because I can cite some examples. Actually, austenitic stainless steels normally whatever we use, it's tensile strength is actually 500 to 550 MPa, and YS is 200 MPa. That means actually it's YS is UTS is actually nearly the double of YS. But when we take case of margin steel, actually it is 1725 MPa is the YS and 1750 is the UTS. That means it is very, very critical. You have to that means there is not much work hardening happening in the case of margin steel, whereas in the case of stainless steel, yes, you can have there is a sufficient amount of work hardening, because it's actually there is a gap is there between yield strength and UTS. So this is very, very important actually in this. Taking the design parameter. And design stress is actually nothing but sigma d is equal to n sigma c, where sigma c is the maximum anticipated stress and n is the design factor. Normally should be more than 1. And also we will make sure that the design stress is less than yield strength. The safe working stress is actually nothing but sigma w, that is actually ys by n. Ys is actually the real strength, where n is a factor of safety. Normally we go for 1.5 to 2. So that is the design parameter, safety factor of safety normally we take. So this is the typical stress strain curve. Actually we have brittle and ductile materials, so which you may be knowing. So the area under curve is actually your fracture, with toughness actually. So brittle material have a lesser toughness than ductile have more toughness. Then we come to the Ashby charts. So this is actually I want to highlight. I've been working on all our time only on this area. My younger brothers, you should work on this now. Okay, because we are done enough and enough. So now it is your duty to enter into these areas. It's still we have a lot of scope here, but some gray areas are there in composites and ceramics that you should address, because the world is going in that way. So let us see. This is we need here the left hand side corner top, that will give the best material. So we have composites and wood products actually giving the best young best and light and higher Young's modulus material actually, right? Many applications need stiff materials, bicycle frames, roof frames. So we need stiffer material in the left hand side corner. So there actually for air, space application, we need low density material to get the payload. So this is the area we have to work. People have already started working on that, but not much good results are not coming in. Good. Next is actually strength density. Here also specific strength we call. There actually the again left side corner composites and ceramics and coming better thing actually, and we should work on that. We can make a composite out of ceramic and metal that will give a better results, but that part is also in progress elsewhere. Among metals actually aluminum, magnesium and all actually very good because lightweight. And in fact, actually, people are doing a lot of metals composites that also giving very good results. Then we have strength toughness. Okay, now having told everything, strength and toughness, we have composites and ceramics core, but they actually lack in toughness. I told earlier, actually, it is not strength, but toughness is also required. This combination gives the best application for space. If you have good strength and toughness, very good. So in that actually, they're actually metals course. They're only, I told, they're only we have to work. My younger students actually should work on ceramics and glasses and polymer, what do you call it, composites to make a material which is in line with actually our metals and alloys. Among metals and alloys, actually we have titanium, nickel are the best actually. In fact, actually some of the high nickel is advantage with nickel is actually nickel is the only alloying element in steel which gives the toughness. So all nickel containing steels are actually showing very high toughness, and nickel alloys also give high toughness. Then we have strength elongation. This is very important. We in fact actually we want the right corner. This corner is actually good. So there again metals and alloys dominates over all ceramics composites. Here actually it's strength and elongation. Elongation is important because to form a shape, to form a component, to form a make, all forming operations actually elongation is very, very important. So strength elongation is very important, and strength is also required. So this combination, we have the best things are actually still metals. So long way to go. And then we have specific stiffness and specific strength. Again, here you see when you if you forget about toughness and elongation, ceramics scores or all materials actually followed by composites. So this is the future. We have to make ductile ceramics, and which will give specific stiffness as well as strength, and we can also meet most of the high temperature applications. Okay, having said all this, let us see what are the conditions by which will decide the selection of a material for cryogenic applications. Yeah, as I mentioned earlier, actually most of the BCC materials, actually iron is a BCC material, 0.45% carbon steel is a BCC material, 0.6% carbon steel is a BCC material, whereas nickel is an FCC material. Nickel actually the impact energy in fact slightly increases when you go to low temperature, whereas most of the BCC material it become brittle at this point, somewhere here minus 1 degree centigrade. That means it cannot take any dynamic loading. That means if you put a iron or a steel in a low temperature lower than even minus 100 degrees centigrade, any dynamic loading in an impact loading can actually break. So we cannot use it. BCC material we never use at low temperature, but there are some exceptions. Then if you do a tensile testing, actually what we see a BCC and FCC material, you test there is not much difference. But when you test the YS, actually you see FCC material there's not much increase in YS, but BCC there is a very big increase when you go to low temperature. So that means at some point the YS and UTs will merge, and that is a point actually material will become totally brittle. So we have all FCC means actually all austenitic stainless steels, copper, aluminum alloys, nickel alloys, silver, etc. Everything are FCC, and BCC ferritic and martensite steels, columbium, iron, chromium, molybdenum are actually BCC materials. HCP is actually titanium, zinc, magnesium alloys. And strength tends to increase at low temperature, and there is a slight improvement in fatty properties at low temperature. 300 properties are actually more conservative. Means actually it is more steady. It doesn't vary much from specimen to specimen, but low temperature actually it varies because of the defect in the material. Any defect can actually pop up the value of the tensile test result. DBT problem is actually most of the material BCC materials have it. modulus increases with the low temperature. So this is earlier I was telling, even though BCC material I cannot use for low temperature, this the addition of nickel, especially in 9% nickel, if you add, actually the complete DVT will disappear. In fact, actually, I have shown it is up to 8.5%, but 9% is completely removes, and that BCC steel can be used. For example, have you heard of LNG gas line pipelines? They are using actually 9% nickel steels. Actually, that contains 9% nickel steel, which is actually can there's liquefied natural gas methane. It can take up to I think it is about minus 110 degrees centigrade. So they can easily take handle that temperature. So nickel is not only it improves the capability of any BCC steel at low temperature, and it also improves the toughness. That is importance of nickel. See the case of carbon. The moment you add carbon in a steel, actually the DVTT in fact instead of going down, it advances. Actually. That means adding carbon means actually it will become more and more brittle at low temperature. Then these are some of the material failure happening at low temperature. We have 316 austenitic stainless steel. Normally, when you test at 4K, that is actually helium temperature. Then if the failure origin is actually poor chromium molybdenum with stone. 6L for titanium, it is alpha phase, XB phase for 77K and 4 Kelvin. Alpha alloy, it is actually at 4K, it is fine alpha phase, the crack origin. Inconel known as super alloy, which we are regularly using, it's niobium carbide. Is the one, it's actually it's not a cryocompatible precipitate. Then 219 is actually precipitate in the granular area. Actually, there are only the crack origins. Then for low temperature, this is my view. I mean, I already made most of the cryogenic materials in for ISRO. My view is that actually for metallic materials there is no UTS and YS specification about. If you see any standard AMS specification, there is no specification, because when I test a specimen at room temperature of any material, I mean steels, of course I'm discussing about steels, I get a very consistent value at ambient temperature. But the same specimen, if I take it to low temperature up to 77K, that's LN2 temperature, I get a different values, because a small defect or a small discontinuity or any defect present in the gauge length can alter the value. So that means actually we don't even, suppose even carbon in industrial amount is locally present also can change the value. So the properties of UTS and YS are very sensitive to the defects as well as the deformation state. Suppose I do some cold work, I mean, it don't be a cold work and elastic deformation and test it, then also value changes. So I don't have a fixed value. So what we do at cryo, all materials gain strength and lose reductive gain toughness. So I give more importance to the toughness testing, that is impact testing, fracture toughness, NDS, that is notch tensile testing. This ratio should be more than 1.1 at cryo temperature. If it is more than 1.1, I mean, it is safe. So the modern way of testing is actually do a fracture toughness testing and evaluate the value. See that actually it is this evaluated value, the stress available that particular crack is can be used for our application, then can be used. But mostly the easiest way is actually do an impact testing. Recently there was when I was in LPS, there was a query. Normally we don't use 7075, which is a aluminum zinc magnesium alloy, high strength alloy. We don't use in low temperature application because we have 2219 and other materials are available. But somehow people wanted to use this material. Then they asked me. Then I done the first test I have done is impact testing. Impact testing I found it's got a very good value. Okay, you can use it safe. There is no issue. Like that, actually, first screening is actually go for impact testing. Then if it is a pressure vessel, go for a fracture toughness design. If it is impact testing, then you can use this room temperature YS and UTS and make your design, so that actually you'll have a sufficient margin. And the fracture toughness testing can be used for cryo process. Then these are some of the fracture toughness values of various materials, aerospace materials. Then we have titanium 6L4E, titanium alloy. This is inconel solenoid, alpha alloy. And what I meant to say, actually, mostly all FCC materials showing actually very, very high value. C200 and 250 is margining steel because of containing 80 nickel, they also show a good amount of toughness at low temperature. Doesn't mean that actually you do not use marine steel for a low temperature application. It can be used, but it is a costly material. We have other materials available, so we don't use it. Then another physical properties available is that actually we have thermal contraction and expansion. This is happening in low temperature. Then what we have actually large amount of contraction actually occur when materials at cold at high temperature. So this impact on the alignment. So different materials have different alpha value, and development of interfaces gaps due to dissimilar materials, increased strain and possible failure, and phase transformation. So some of the things can happen with the thermal contraction. Specific heat normally CP decreases, and it has got two important points. First of all, system cool down faster as get colder. At the cryogenic temperature, the small heat leaks can cause a large temperature rise because of the low CP. Then another important thing is actually the electrical resistivity. Low temperature, most importantly at room temperature, it may not be noticeable. When you go to low temperature, the purity of the material becomes very, very important. So there is a residual resistance, resistivity ratio is there, RR. It is the resistivity at 300 grade divided by resistivity at 4.2. This shows the purity. Purer the material, it shows very high thermal, electrical conductivity and very low electrical resistivity. This is the basis of superconductivity for metals. Then thermal conductivity for high RR value, it increases at low temperature. Most of the alloys actually it falls down. We have a relation between electrical resistivity and thermal conductivity, and then it's known as WFL law. Then that's about how do you select a cryogenic material. So we go for a impact testing and use the room temperature YS and UTS value for the part design. For high temperature, it is very interesting because we have most of the materials actually, okay, we are storing the propellants and it's firing, so many materials are exposed to high temperature. High temperature, actually, we have again ceramics dominating in the RCB charts. And among metals, actually, nickel is the best material. FCC alloy, nickel-based alloys, and cobalt-based alloys. All FCC materials are actually best. We have all other materials are actually not good. Again, ceramics can be used. So what we use actually a combination of alloys plus ceramic coating we use to increase the maximum surface temperature. Okay, this is all about our space materials. What can be used or what is being used. Here it is there. So we will start with from here, left side. So aluminum can be used up to maximum 100 degree. That's all, and some composites can go up to 200 degree. That's all. Then titanium alloys up to something like 500 degrees plus, and titanium aluminate again up to 700, 750 degrees centigrade. Super alloys, lot of development. Every 6 months I am seeing a paper for super alloy development. It goes maximum at present the best super alloy can go up to 1200 degrees centigrade, and precipitation hardening alloys actually can go up to 850, 800 degrees centigrade with a very high strength. It retains strength up to 850 degrees centigrade. Then here actually we don't need any oxidation protection coating because superalloys contain actually a lot of aluminum and chromium, so that will protect the material from oxidation. From here, actually, whatever we have, well, refractory metals, ceramics, graphite, all this actually needs a lot of protection coating from oxidation. Oxidation actually. So graphite we give silicon carbide coating. And so refractory metals actually give special coatings actually which will prevent the material from oxidation. So we use a lot of refractory materials like columbium, molybdenum, etc. I mean tantalum also we use, but columbium is the lighter, so it's more preferred and is easy to deform. So they are the most preferred refractory alloys. And then one of my dream materials actually which I want to do some work is actually rhenium with iridium liner. Actually, this actually can go up to 2200 degrees centigrade. This actually used by NASA for all their outer space missions actually. So all this because 2200 degrees is very good because With columbium, actually maximum we can go to 1450 to 1500 degrees centigrade. So this is very good actually. Graphite, carbon-carbon graphite composite actually used for all regenerative vehicles because it can go up to nearly 2000 degrees centigrade, and with silicon carbide coating, it can go further. Then one of the important thing about the high temperature is that actually it has this creep issue, which actually space we don't have an issue, but even then you should know about creep. Actually, the creep is actually nothing but the deformation at a constant different temperatures at a constant stress. You can see at 70 MPa, 600 and 650 degrees centigrade, we don't have much issue. But when you go to 700 and 675 degrees centigrade, material deforms, and these are some of the mechanisms: separation, slip and climb, grain bound sliding, diffusion flow. So one of the prominent things is actually grain bound sliding. So what we do actually, we do make a coarser grain material so that actually the grain bound sliding will be difficult. So this is the principle of actually single crystal and coarse grain material. Then, how do you make a high temperature material? So we have 2-3 techniques are available. First of all, we go for a salt solution and hardening, like in the example of actually your cobalt alloy Haynes 25. There actually molybdenum, tungsten, hafnium, everything has been added so that actually it will give a salt solution strengthening, and it is not heat treatable. Just ideally can use it. It will work up to 1100 to 1150 degrees centigrade without much issue. With a coating, it can go up to 1200 degrees. Then but the strength of the material is very low. But if you want strength, then you have to add precipitation elements like aluminum, titanium, and iridium. That will work up to something like 850 degrees centigrade maximum. That is the latest alloy development. 718 will go up to 650 degrees centigrade. So then we have another technique that we add carbides. So we have when you add carbon to a limited amount, too much carbon, it will become brittle. So carbon in the presence of chromium, titanium, and molybdenum, tungsten, this form actually this will avoid the grain bound sliding and deformation to retain strength also. So that is one technique. Next is actually we have grain structure, coarse grain. When we have a high grain aspect ratio, it will avoid the grain bound sliding. Then the third thing is actually dispersed strengthening. That is only the one area where actually we have a lot of PM2000, all this material actually showing with them capability up to 1200 to 1250 degrees centigrade without any oxidation and all issues. This is very good. But only thing is forming, welding, joining, and all actually very difficult. But it's been used. Okay. That is one thing. Next thing, actually, some techniques by which actually you can the thermal management can be done. Okay, this is our liquid engine, restorable liquid engine. We call it because it looks beautiful, right? It is shiny. This is a cobalt alloy. Okay, so what happened? Like this looks very shiny, beautiful, but actually, operation or heat transfer point of view, it is not good. Why? Because actually, our engine is going to work in vacuum. So when in the vacuum, what happens actually, your MCT is actually it is without coating at room temperature, it will be 0.42. Okay, so when the actual operation actually, it will never increase from 0.5 to this one. Maximum 0.5, it goes to 1000 degrees centigrade. This has been tested. This test has been done in air. So in vacuum, actually, with air actually, this oxidation will happen because of the actual MCT increase. So this is your Stephen Boltzmann law, which says temperature to the it's proportional to the temperature, fourth power of temperature actually, and this is the MCT. So MCT, to bring down the temperature of the material, the outside temperature, because here the melting point of this cobalt alloy is actually very close to 1300 degrees centigrade, and the temperature developed inside is actually very close to 1150 to 1200 degrees centigrade. So imagine if it's a shiny surface like this, actually heat transfer, and the only mode of heat transfer is radiation. So if you give a shiny surface like this, actually it will transfer will be very, very poor. But instead, if you give a surface like this, and if you give a emissivity coat like with 0.80 emissivity, it will approach 0.90 or even very close to 1. So that means actually the transfer will be very good and that is safeguard material. This is very important. If you see any launch vehicle outside, actually, you see a very dull surface outside. I mean, if it is for a radiator, there are two kinds of coolings actually happening. One is regenerative cooling. The regenerative cooling, nothing is required. But when you are cooling with the radiative cooling, actually, like this, it's a single sheet. There is no, sorry. Yeah, when you have a single sheet actually and heat has to transfer to the atmosphere, then actually we need a dull surface outside. So this only we need a dull surface like this, which will give a emissivity as high as 0.8. Good. Then we have, that is about the heat escape to the outside. Now, in suppose water during combustion, the temperatures are reaching, as I shown earlier, 3000 K. Now, to arrest the heat transfer to the material, the chamber material, what we do is actually we have to give a coating, ceramic coating, which I was telling. Ceramics, especially zirconia, has got a good thing actually. It has got a poor conductivity of one watts per meter Kelvin or less. So this will actually eventually break the heat transfer to the chamber material. The two kinds of coatings there are. It has been done like this. First, this is the substrate material. This is the bond coat, or bond coat actually we will have the ceramic coating. So bond coat normally it's nickel aluminate or kind of combination of many metals actually, and ceramic coat will be based on zirconia. There are two kinds of zirconia available. One is actually calcia stabilis and one is yttria stabilis. Both will actually prevent the material being heated up from the hot gases actually. Normally in our engine actually we get about 50 degree to 100 degree margin. That is very good. And this you can the comparison has been given. And interestingly, this we call nickel chromium aluminum nickel, and this is 8YZ. This has also been used by our aircraft. I mean, all Airbus and Boeing. They are also using. And in fact, actually, Air India has got such a coating facility available in Bombay. Not only Air India, many people. ISRO has to put one. Bangalore. Every city has got a coating facility actually for this thermal barrier coating. We call TBC, that is thermal barrier coating. That is coating, that's the name of this coating. And it can really prevent the material from melting. Then, this is very, very important. This is, in fact, this is my own finding or my own idea actually. Normally what happens, whenever I want to test a high temperature material, imagine I want to test at 1000 degrees centigrade. It takes my machine, normal UTM takes nearly 1 hour to test, get the temperature and test. In fact, our mission, whatever Vikas engine or cryogenic engine, Vikas engine I'll take, it's a radiator cooled engine. The maximum duration actually 150 to 200 seconds, depends upon the range. So, my material, to test the material property at 1000 degree, I need 1 hour. By 1 hour, actually, the material will be very soft and it will give a lower value. So I just wanted to know what, suppose if I can test the material in 150 seconds time at 1000 degree, that will give a realistic value. So that's what I have done. So here actually the conventional testing is like this actually. Heating time, it takes a lot of time, almost 4000 seconds. Whereas suppose I can test within 10 seconds, then my material property will be a different thing, I'm sure. So let us see. I have installed a machine called Glibble, where actually where my heating rate is actually almost 10,000 degree per second. So with that, actually, I could do the test. So what we found actually that the high temperature alloy which we have used is a cobalt alloy, and initially we had done at 1150 degrees centigrade. That's the maximum temperature we expect in that our normal operation. Then we had done at 1200 degree, which is margin. Again, 1250, 100 degree margin. Even every 10 degree margin is very, very important. And what we do actually, within 10 seconds, I reach this temperature. And I keep it for the entire mission period of 200 seconds. Then I test it. That means after exposure only, I've taken the worst case of testing. Interestingly, I got a very, very interesting results. that at 1100 degrees, suppose I do a test conventional way, I get only 92 MPa and UTS and 61% YS. Elongation will be very, very high. And if I do the same thing with the actual flight conditions, so what are test pattern I shown is actual flight condition, I'm getting 208, 208 plus 137 YS. So even up to 1250 degrees centigrade also, I'm getting a very high value. 1250, or I could have gone more than that actually, but then the problem is actually it is never warranted. So that I didn't do. So what I mean to say actually, since we are having a small what you call flight period, actually 150 seconds, the material is retaining most of its strength. But this is not, suppose you are increasing the time 150 to 600 or 500 seconds, the strength value changes. But for at present, the launch vehicle missions we are using actually, this is the margin we are getting. We have sufficient margins. Okay, there is no issue with the. So what I mean to say actually, if the composition is ensured, material gives such strength. Then we have an environmental issues. Having told about cryogenics, high temperature, come to the environmental issues. Before environmental issue, actually, I want to tell something about the how a liquid engine is actually working. Sorry. Yeah. Here actually we have oxidizer, we have a fuel. Both for a storable as well cryogenic engine or semi-cryogenic engine, this is same. Then from oxidizer, actually using a booster pump, it comes to the main pre-burner. This is gas generator. Okay. From fuel also same way, fuel booster actually comes to the pre-burner. From pre-burner actually it generates the hot gases, burns there. There is an igniter, it burns there, and that hot gases actually will come to drive the main turbine, which will actually give the propellant and fuel to the combustion chamber. This is the combustion chamber. Okay. And sometimes what happens, the same hot gases after driving this one, it will endures here also to save the fuel and the temperature. So what happens actually in the cryogenic engine, we are actually using, it will be rich in hydrogen. In the case of semi-cryogenic engine or any new engine, sorry, semi-cryogenic engine, it will be rich in oxygen. So these two combinations actually totally change the concept of materials actually used there. So we'll go into that. First, actually, we'll discuss about the effect of hydrogen. So hydrogen actually is, the best fuel. And in fact, actually, why I'm telling, in fact, Tata has already started working on that. Actually, my dear students actually should see what are the materials useful for, because many people may, this is not an area where people have worked at. So this is a special area. We should put some light on this. It will be very interesting. Hydrogen is the best fuel compared to gasoline, diesel, or even LPG or ethanol. And the energy per kg is much higher compared to all these. Then, issue with the hydrogen is actually, I'm so sure maybe within 5 years time from now, hydrogen cars will be available. It will be cheaper than your electric cars, and it will be more greener actually, because electric cars, the portion is actually for generating electricity. You need, because Kerala has got hydro electricity, but other places actually still you have to burn the thermal power actually. So again, that way you're polluting. But the hydrogen is actually, you are giving a green, what do you call, out product, that is water. So combust gas, gas high pressure is some issue, storage. So but that has been solved. Now we have actually up to 150 liter tanks, ready-made tanks are available. Then solids storage with hydride, material and thermal problems. We cannot store it for a long time. So a small experiment we can do, but commercial purpose it is difficult. Liquid storage, again, the problem is actually maintaining that temperature is actually big issue. So only left is actually compressed gas, high pressure, hydrogen. So all these issues have been initiated by NASA. So what happened actually, NASA from the tank minus 250 degrees centigrade comes out, it comes here, burns, then comes here, drive the engine. Then by the process actually, the temperature, it picks up temperature, it goes as high as about 823 degrees centigrade. Then again, and there see, what I mean to say, actually, from minus 253 to plus 823 degrees centigrade, it picks up the temperature at many regions. These many regions, actually, the material will have the different materials materials are used and it's exposed to hydrogen. So whenever you see a hydrogen issue embrittlement, actually normally people will be telling about the hydrogen embrittlement caused by the internal hydrogen. That means hydrogen which has been deposited along with electroplating or hydrogen dissolved within the metal, actually the cause for internal hydrogen. Whatever I'm talking is not that. This is actually exposure to the hydrogen gas. That means minus either it's liquid hydrogen or gaseous hydrogen. So GH2 or LS2. So in SSME, it operates in, nearly 520 seconds and in the space shuttle flight, and it is designed for 55 engine fires, and life is actually normally more than 7.9 hours total. So we have hydrogen. Normally whatever hydrogen, internal hydrogen, whatever I discussed, actually the failure normally happens in the form of delayed cracking failure. Delayed means actually hydrogen enters the material and after 1 or 2 days or maybe a month or in a week it cracks, okay, fails. But this is different. Gaseous hydrogen is actually that India, we don't have any facility to do test this gaseous hydrogen effect. In fact, somebody started in Bombay, but they withdrawn because it is not safe. But there are a lot of data available from NASA. What they're finding actually, like any tensile testing, you introduce a chamber in that you fill the hydrogen, increase the pressure and see the different pressures, the mechanical properties. The result is imminent. The moment you test a material in hydrogen gas, the material becomes suddenly brittle. It's not a delay, immediate thing. And so many materials have been classified as extreme, severe, and slight and negligible. So based on that, actually material has been selected. Hydrogen on susceptible materials are, we call actually HEE, hydrogen environment embedded, lowering of ductility and toughness, surface cracking, subcritical crack growth, fast cycling, and sustained crack growth. These are the immediate effects. So why I'm telling all this out, okay, forget about the rocket engine and the rocket fuel. This hydrogen, when you are going to use as an automotive fuel, actually, this is going to be very important. This whatever I'm talking about is very, very important because hydrogen gas handling, especially knows, your valves, your lines, tanks, there is no issue because we have got aluminum tanks available ready-made. But the lines, hydrogen lines, actually, you have to take with the material, very good material actually, especially the valves. Valve material is going to be important. So we have categorized the most extreme. You can see that, right? Extreme, severely, and slightly and negligibly brittle material. The worst material is actually marine steel, and almost all marine steels are bad. Inaugural 718 is like the material used for all rocket engine. They are also bad. But NASA has been not telling actually how they are managing it. But I am sure actually they are giving some coating wherever actually high pressures of hydrogen is coming. So the effect is actually mostly happening at room temperature. Room temperature, what happens actually from minus 50 to plus 150 degrees, the maximum degradation is happening. If you go to very low hydrogen temperature, no issue. Very high hydrogen also, there is no issue. It doesn't happen. But the effect is happening when the hydrogen is exposed at low temperature. Now, then you will be asking why ISRO doesn't have an issue. ISRO doesn't have an issue because our hydrogen pressure is actually less than 10 MBA. That means nearly 100 bar. So we don't have much issue. We are somewhere here. Whereas NASA they are somewhere here. So they have a real issue, but they manage with the help of coating and selecting of special materials actually, which they are not disclosed. Okay, good. Then we have this is the stress intensity. Everything comes down. Fracture toughness, all this comes actually comes down. So 718 actually they have done some coating and they found out they have solved the issue actually. So these are the materials actually which are shown on the table. So we have negligible materials actually, aluminum alloys, caustic stainless steel, A2H6, OFC, copper, and that has been. In fact, based on these first principles actually, in fact, I have developed a material. It is yet to be used. It is in my, it is one of my pet development which I have done in NPC, which I'll discuss late in this presentation. And we have prevention is actually one is gold, silver coating, cadmium, aluminum, all these things are actually very good. The coating with low hydrogen permeability, non-porous, completely adherent, and ductile and self-healing. This kind of coating can be helped. Nickel, chromium cannot be used for this application. Then we have gas bottles available actually for storing hydrogen. Why? Because I am telling you, these are readily available. What they do actually, there are type 1 is actually fuel metal tank. Type 2 is actually a grit wrapped with Kevlar. Kevlar is actually composite. Then fully wrapped with the carbon. Then it's a fully polymer liner without any metal, with metal ends and without any liner. So this is the type 4 is the lightest. In fact, we are using type 3 gas bottles actually for storing gaseous hydrogen. Then second, having told about hydrogen, then it comes the oxygen. Oxygen, you think actually it's a very, it's our material gas which we are breathing actually, but it's more dangerous than actually hydrogen. I normally ask in many of my classes actually, when I take classes for my my colleagues in ISRO, I normally ask, I have a room full of oxygen and one room full of hydrogen, which is more dangerous. People will say hydrogen is dangerous. No, the oxygen is dangerous. What happens actually, anything will become fuel to oxygen except oxides. So we don't have till today no engineering materials actually available to resist oxygen ignition. That's very, and we have some engines actually where actually the oxygen, hot oxygen is coming from the pre-burner and the gas generator to drive the turbine and come to the main engine. So those area has to be protected from the attack of hot oxygen. Now, metallic metals ignite in oxygen atmosphere under certain conditions. Compatible LOX, we don't have any issue. Only GOX, gaseous oxygen, is an issue. Accidental fires do occur in oxygen system because it enhances the combustion. And okay, some of the things, important parameters actually for oxygen ignition is something like this. We have fuel, anything will become fuel. So suppose imagine the heat of oxide formation is very high, like aluminum, beryllium, and all actually, then it will immediately ignite. Suppose the thermal conductivity is very high, like copper, the ignition chances are less. The thickness of the material is high, it doesn't ignite that fast. For example, your oxygen storage tank, they are very thick. Even the ignite happens, it doesn't, it will conduct away actually, whatever heat generated connect. Contamination, some carbonate fuel actually, that also will accelerate the ignition. Oxygen, come to the oxygen status. The temperature is high, yes, it is more prone. Pressure is high, yes, more prone. Velocity is high, more prone. Purity of oxygen, yes. Phase, if it is liquid phase, we don't have much issue, but if it's gaseous phase, yes, it's a problem. Then the ignition conditions are actually, the energy released from the second material can cause ignition. Particle black, that is the mostly we are troubling us actually, because aluminum particles are coming from the tank and it can ignite the, it can hit it in the side wall where oxygen is actually traveling. Friction can generate heat and it increases the temperature of ignition. It crosses the ignition of temperature, then it can cause ignition in under oxygen condition. Electrical energy, adiabatic compression, and gases, all this can cause this one actually, ignition. So oxidation is a slow burning of material, whereas ignition is actually thermal instability, catastrophic failure can happen. Yeah, very practical example I want to show you. If you just Google it, find out burning of ambulance 108 emergency. Many things. It has happened in Trivandrum, Calcutta also. I didn't go there, but I read from this one actually. The entire vehicle is actually got fire, and the diesel tank is intact. There are electrical things are intact, but material is, the vehicle is simply burning. They don't know from how it is burning. They put water, nothing happened. It is completely damaged. So the finding out is actually they found out that actually this is happening in Coimbatore. They found out actually the oxygen tank which is kept in the vehicle actually it got leaked, and by movement by traveling actually in our roads are very good actually, because the travel actually hit on the side and small rubbing has happened and generated heat. That heat actually there is a factor called ignition temperature. The ignition temperature it is toast and it became became ignitable. It caught fire. So paint is it caught fire, and finally the vehicle has caught fire, and it started burning. The metal became the fuel to the oxygen. Oxygen supply is already started, so it becomes the fuel. Actually, the vehicle has become the fuel to the oxygen. So This is the ASTM standard, which says which are the best material for and the worst material for oxygen application. We cannot use magnesium, beryllium, calcium, and titanium, zirconium, hafnium, and aluminum also is a part of that. Actually, this aluminum, yeah, aluminum also generates a lot of oxide, heat of oxide. The best materials are actually nickel, copper, palladium, silver, platinum, and gold. In fact, actually, palladium, silver, platinum, gold, we cannot use it. We can give a coating maximum. They are not engineering materials. So, most of the material for oxygen applications are either waste on nickel and copper. Till today, we don't, only SpaceX and Blue Origin team, that is actually Jebro's Blue Origin team, they are working on this material, and they almost frozen the composition, and I don't have any idea what is the composition of the material. Because I know this much, actually it's a nickel-based alloy. They have developed an alloy which can actually resist ignition for oxygen at temperatures as high as about 800 degrees centigrade. And then they'll be asking till now, because the only engines which has been, we call as actually oxidizer rich pre-burner, we call oxidizer rich stage combustion, we call. That means oxygen rich stage combustion. Only Russians have mastered. There is their engine called RD-170, which uses actually hot oxygen. So what they have done is actually, wherever hot oxygen is coming, the entire area they will coat with oxides. The entire oxygen path will be coated with oxides. And with that, actually, they successfully made so many RD-170 and RD-180 engines. In fact, they are the only successful rocket engine people in the entire world to use oxidized stage combustion. And so NASA wants to avoid this coating business. So they had invested a lot of money, found out. I know one Dr. Monica. She is actually a part of employee of Boeing. Last 15 years, she has been working. She made an alloy, but unfortunately, the forgeability of the alloy is so poor. So finally, what they done actually, they made a powder of this alloy, and through 3D printing, they made the turbopump and accessories. Actually. So that their engine also ready. And what SpaceX has done is actually, SpaceX has made a casting of this alloy, so that because workability is so poor. One casting they are made, which they are machined and used in the form of a turbopump, where hot oxygen is actually passing, and that I think they will be using their new rafter engine. So in nickel alloy, the thing is actually, suppose the nickel alloys, these are the common alloying elements. So in nickel alloy, when you add aluminum up to 5%, no issue. We have a pressure at which actually burning of oxygen is happening up to 69 MBA. That is good. The moment it touches 10%, it comes to 2.0. Like that, actually, iron can be added up to 20%. Chromium can be added up to 20% without any degradation. Manganese also can be added up to say 9.10%, and silicon can be added up to 10%. Titanium actually maximum 5%. So like that, actually, these are the first principles. From that, actually, my colleagues in LPC already started working on to develop a new alloy, because for that, actually, a lot of because one problem we have actually, we don't have facility to test the high pressure oxygen on at high temperature. This is available only in our engine facility, testing facility at Mahendragiri, and it is not a joke to test high pressure, high temperature oxygen. So this is only challenging work how to test this one. Actually, we don't have the facility. Alloy can be made, but we have to test, make a lot of compositions, then only we can optimize actually. So that it is really hurting us. Yeah, then we come to materials and processing. In that, actually, I'll some new alloys we will discuss why we should. We are also venturing into that. As I mentioned earlier, actually, Space Shuttle actually used aluminum lithium tank actually for storing liquid hydrogen and liquid oxygen. So we have why this lithium is important is actually lithium addition to aluminum gives the highest reduction density and increase elastic modulus. Every 1% of lithium, aluminum alloy, the weight density comes by 4% and 3%, and the modulus by 6%. It gives very high strength, modulus, specific strength, and density, low density, and good formality and good conversion. Only problem is actually joining. Joining is a real issue. because it can be joined only by friction stir welding. Normal fusion welding, it is not possible. In fact, this is a topic you can really study. Aluminum lithium metal can be made available to you. Find out an alloy composition where it can be fusion welded actually, because this is a challenge. FSW, the problem is actually we have facility in our HAL Bangalore, where actually you can make up to 3 meter we can make. But only thing actually we have this fusion. Somebody can make the fusion welding. Very, very interesting. In fact, literature says actually aluminum silicon alloy can be used, but I don't know. I didn't do any experiment on that, but this is a very challenge. Why I'm after this one actually? If I'm using, I told you 1 kg of payload is nearly $20,000. If I use for C10 GSLV Mark 3, that's our cryogenic state C25, if I change from 2219 to 2195, this is aluminum copper, that is aluminum lithium. If I change from 2219 to 2195, I can increase a payload very close to 250 kg. So imagine 250 into $20,000 is a huge amount. So that much payload gain, and it's not a joke. So we are working on that. Only thing actually, these are some of the properties actually. It has got very good properties, and density is also more. Density is also much less compared to 2219, and we go and higher density coupled with a higher strength. So that is the interesting thing actually. So aluminum lithium, you will hear one day actually, maybe not now. You will hear ISRO has actually switched out to aluminum lithium for its cryogenic tanks. Then another important thing actually, how to make a cone. So one of the techniques actually cone is actually because every material, so normal aluminum alloy you can make a cone, but a special alloy cone making is actually very difficult. So we have something a new technique called flow forming, which we because of my pressure actually many of the industries, at least I know 3-4 industries are already invested in and they are already making it. If you please, when you go to home, find out, check your cooking gas cylinder actually. They're actually flow formed cylinder actually without any long seam weld. Okay, these are some of the techniques actually. You can make either a cone or a cylinder. In India, actually, we can make cylinders up to at present 700 mm. 1 meter actually people are already making the metals. So the technique is simple actually. We mount a small ring here. Okay, and ring will be actually the outer OD of the ring. Ideally will be same. OD of the ring will be flown over this pattern and make a tube. So already we have made actually. In fact, actually, interesting thing. This is the easiest technique to make a missile. In fact, the best experts of the up to 1 meter class, the experts of the flow forming people are actually from North Korea. Imagine that. No wonder why they are making so many missiles actually, because these are very simple to make a case. You make the cylinder, fill with the propellant, your missile is ready. Okay. So in performing, it is only thing actually you gain strength by flow because it's a cold work operation. Gain strength because and if you age it like marine steel and will be fantastic actually, because already our Bharat Dynamics in Hyderabad they are doing it. Many of our missiles actually the material is actually marine steel. So that is the very important process actually. Already 3-4 people have already invested in this. I know 5 people in India can make up to 700 mm. Then some of the new materials actually in ISRO LPSC actually I made a lot of materials, especially for cryogenic engine and semi-cryogenic engine, loss corrosion engine. But among that actually for every football team, you have a special player actually. Like I'm a fan of Cristiano Ronaldo. So like that you have many actually. So like that actually out of all these materials actually some of my pet materials which are developed actually I'm showing you. First one is like a copper alloy. This is actually used in the cryogenic engine. So whenever a GSLV or a GSLV Mark 3 goes up, it's my material. I'm proud of that. It is my material. It is actually flying. Okay. So importance of the copper is the alloy is that actually this is channel melt. So there will be outer cover will be there on this. It will be brazed. So through the channels actually liquid hydrogen will be flowing, and the inside temperature is actually as high as about 3,500 K. And the copper temperature, maximum temperature, because of the liquid hydrogen, it's a regenerative coating. The copper temperature will be as high as about 600 degrees centigrade. So this is the entire world actually, even NASA or ESA or Russia, everywhere actually same thing only used. Some of the material properties required for this material is actually high thermal conductivity, because I then you will ask, you can't use what do you call nickel alloy. Nickel alloy high strength is there, but problem is actually conductivity is so low. It is only 10 to 12 watts per meter Kelvin, whereas copper is actually near 300 plus. So because of thermal conductivity, metal doesn't melt. Low coefficient of thermal expansion, able to retain strength at operating temperature, low cycle fatigue strength and bit creep life, compatibility with the liquid propellants, especially hydrogen or kerosene or oxygen, whatever it is, and then high UTS-YS spread. That is also very important. That the big material, even if it yields also, it doesn't come to cross the UTS point. Then this is the material which I have done actually. You see, now there's a small correction actually. UTS is actually 170. Sorry. So this is the NASA material developed by NASA, and all the three materials actually I worked, but I found this is the easiest material I got, because this material shows it can be easily formed, and make it into any shape, whereas this offers a better resistance to deformation and difficult to forge and all actually, because we are not successful, because it needs a special facility called isothermal forging, which we don't have in India. Then basically GR-COP84 advantage actually it does it actually gives it's a polymer product, and it doesn't lose it doesn't lose the strength at high at high temperature for multiple times. So it's very good. So GR-COP84 is actually very good. Only problem is it's a polymer product, but with the coming of 3D printing. With 3D printing, actually, it can be this can be made into any shape. Actually, already NASA has entered into this activity. Then this is another high strength material. This high strength material actually, which was developed by me. Actually, it is actually a substitute to maraging steel, which is actually stainless steel containing stainless steel properties. With all maraging steel behavior actually. So we have composition actually like this. Actually, it contains chromium and brought on nickel. And maraging steel, one of the issues that actually when you make a fastener or any sharp notched application, it fails because of the SEC issue. And the Kevin SEC is so low, it's less than 20, whereas this material has got a very high Kevin SEC, which I already which I already made and supplied, and we formed strips active for making into Merman band of our active satellite suppression system. So this has got a very good properties, and all properties of maraging steel with stainless steel, which was one of my dream material. In fact, actually, when I worked with Dr. Sinha and Sri Kumar, actually, we were having a dream. Before my return, I made it all right. Thank you. Then another thing is actually a nitrogen containing bearing steel. Actually, in fact, actually 440C is the material traditionally people are using it, but one problem is actually it has got primary carbides. These primary carbides can cause a cracking like this actually. During, after some storage time, and that causes a lot of issues, a lot of failures happen actually. So what happened, we brought down the carbon from 0.1% to 0.37 to 0.0%, and we added nitrogen to balance that. And it does, because nitrogen advantage is actually it improves the pitting resistance of any stainless steel. So corrosion resistance is superior, and it is in fact actually already I made this material to Starware, and I supplied the rods to my our team in IASU in Inertial Systems for making bearings, and it has got a 2 level of strengthening. I can normal like 140, 180 degrees centigrade tempering, as well as secondary tempering at 500 degrees centigrade. Advantage with the secondary tempering is that actually, tempering is that actually it offers higher toughness compared to the primary tempering, and it gives a higher similar hardness like primary tempering. So you have two options actually. Then this material also been developed and given to my ISU team. Then about the hydrogen application, I made a material See, there is a finding actually, when this has not been found out, the real reason is not been found out. If your nickel content of the steel is actually between this to this, your hydrogen environmental embrittlement is actually much low. So we have developed an alloy actually, and it's made commercially. This is a composition. This is available in ISRO, and we named as actually HER alloy, hydrogen environment resistant alloy. This alloy has been already made, and it can be used for any hydrogen gaseous application like make valve or pipe or gas bottle. Anything can be made. It's been already made, and that has been we are tested actually. We got very good properties. Elongation has been not deteriorated. So we have discussed materials and requirements, materials for cryogenics, material for high temperature, environmental issues, and new material processes. I think given some picture about what I will be doing in LPSC and my team will be doing in LPSC. Because liquid propulsion, we are, as I mentioned, nearly 120 alloys we have been using. Thank you. We have miles to go. Chat out your part. Thank you for kind attention, and I expect some good questions. Thank you.
Thank you, sir, for that wonderful speech. Thank you for informing us all about the topic. If anybody has any queries or questions, please feel free to put it in the chat box.
Yeah, more questions are good.
Hello, Tharian.
Yeah, please tell us. Yeah. Yeah, before pausing, actually, I want to thank my bosses. My boss has been second. There are very important people are there. First is my boss, Sri Kumar. He's my mentor, boss, friend. He's everything. Okay. Then Dr. P.T. Sinha of MMG. He was our DD in GSSC, and my Dr. K.V. Nagarajan was my JD in MMG. In fact, he only told me about all Russian materials. I didn't know anything about Russian materials, actually, the language. So he told me everything, actually. I'm thankful to all these people, actually, because they only made me to make all these materials, actually. Yeah. Yes, Srikumar sir, tell me.
Tharian, this flow forming method, are you practicing it now?
We are actually doing now. We are actually we are making.
Where is it done? Where is it done?
It is done at actually one company called Paras Flow Forming in Bombay. We are to do the thing. Actually, we are done. Pardon?
Midhani is not doing anything.
Midhani is doing. Midhani, their recommend is down.
Okay, okay. Because okay. It was a very good talk.
I don't know, because I'm seeing some. It was not audible actually. I mean.
No. Sound that you would have talked slightly. I mean, it was not that much audible for me. I don't know about other people.
Because I am seeing some messages actually.
Maybe because
I'm sure told me in between actually, because I have a problem. We just recovered from COVID actually, because I have got problem with my throat.
Oh, okay.
My normal. Yeah. Okay.
Let others ask questions. Thank you, Tharian.
Yeah. Thank you. Yes, Amal Jyothi team, especially my younger students, please ask. I'm available here. I'm seeing some 46 participants and nobody is asking. That's not correct.
That is typical of Amal Jyothi.
No, I am asking. Was it a very, I made it very light. No, I don't think I talked too much of metallurgy or science, right? Mostly rocket engine and the applications only I talked. I think it was digestible, right? I don't know.
Yes, Tharian, you made it so simple that everybody understood. Yeah, that is one of the reasons.
Oh, okay.
Yeah, it was so beautifully presented.
I didn't talk any metallurgy or any deep dislocation structure. Simple thing only I talked.
Very good. It is excellent. So people might have understood, students might have understood.
Okay, okay.
Sir, it appears there are no questions from anybody.
Yeah, good.
Yeah, so thank you, sir, for the incredible seminar that you've given us. We are thank you for you. We are very thankful for spending your time with us and guiding us, sir. We hope that you will continue to do so in
But
the future.
I have a comment there. One day after COVID, actually, I'll come there. I want to meet the students actually one day to meet them live because this so.
Definitely, definitely, sir. Hi,
I
sir.
want to come there because this is not correct. The students are not asking any question. What I don't know. They should ask question. Anything is okay for me.
I think, sir, students. Hello, sir. I think it's because of the lunch time. Students are.
No, it is only 12:47.
As it is marine.
Yeah, yeah.
Marine, that is not an answer for this.
As I
Normally, actually, wherever I go, I poke people actually to ask questions. Then only I also feel happy. You know?
Yes, yeah. I will tell the students. I don't know students why students are not asking any questions.
Yeah, okay. I made it simple. I don't know.
I think our 5 years as well as 3rd years are there, but they are not coming up with any questions.
Fine, no problem. One day I'll come. Let the COVID be over. I'll come there and I'll meet them in person. Yeah.
Definitely, sir. That is very wonderful, sir.
Because,
Shri Kumar, sir.
Yes, sir.
Mandal sir, you have any question? Mandal sir?
As I'll ask whether it is my sound is audible or
Yeah, it's
very well audible.
Audible, sir. You may ask, sir. You may
as,
ask.
Thomas, I am asking, those are the material you have shown is, I think in the class we have taught them, but is fuel tank, no oxygen, particular fuel tank, particular shape of the cone of the cone of the your this tank, then this why it is very much ignite that things. If you explain, that is very nice things. Maybe our student they can learn something.
Okay.
Fuel tank is very important. Okay,
fuel
particularly
tank.
oxygen fuel tank is very important.
Fuel tank actually advantage actually the temperature is actually it's a liquid temperature, so there is no issue. The moment the liquid state comes to gaseous only, both the hydrogen and oxygen becoming vulnerable. I mean it is attacking materials. Actually. Fuel tank only requirement is that the material should be compatible for cryogenics. I mean cryogenic application. Like aluminum is an excellent FCC material for storing any cryogenic propellants. There is no issue. It is only storage. But the moment it comes out from there and when it becomes gaseous, burning, heat, then makes all issues actually. Hydrogen both and oxygen both are actually equally not. Oxygen is more dangerous, but hydrogen is actually people are already handling it.
And more about this shape of this cone of shape of this tank is that things is very important. Okay,
they are cylindrical.
Yes, yes.
Cylindrical. I showed you know NASA's one Sesame tank. I showed you know. Cylindrical. It's about 47 meter long and 8.5 meter. But ISRO's thing is actually much lower. It is about 20 meter by something like 4 meter.
Sir, is one of the is your material in copper based like thermal conductivity is very high. You are using
I'll show you just a minute.
Okay, sir.
Very important.
You just
are you seeing my presentation now?
Yes, sir. Throughout I am observing your presentation. Okay.
Fine. I'll show you a very important thing.
Okay, sir. Copper based like
here actually you notice this.
Sir, are you sharing the screen?
Thomas, sir, share the screen.
I'll share.
Okay,
yes.
Rather than all of the at least okay, but copper is very high thermal conductivity as well as.
Yes.
Are you seeing now?
Yes.
Yes, sir. It is.
There is very interesting thing. Whenever I'm sorry. Just a minute. Whenever I'm forming this alloy. Whenever I'm forming this alloy, my yield strength is only 60 degrees. 60 MPa. But when high temperature, it increases. We don't see this such thing material. At ambient temperature, this YS value is low, but high temperature is high. This is a very interesting thing. Because what happens, my material, we make a chamber. This is a chamber actually. Yeah, this is a chamber. So we do bracing. Okay, they would brace foil and we brace and close the channels. Okay. So the brace temperature is at nearly 10,030 degrees centigrade, and after that actually it goes for the engine operation. Actual engine operation actually it's about 600 degrees centigrade. That 600 degrees centigrade actually the precipitates comes out and it strengthens the material. That's why actually we are actually seeing a increase in what you call YS. From 60 it goes to 140, whereas UTS is actually it is not 140, it is 170. I'm sorry, it's 170, and UTS is YS is actually 140. Whereas no other material, no other customer material shows such behavior actually. So at room number 3, I can do any forming, deep drawing, flow forming, any forming I can do, welding, anything I can do. Then finally go for bracing, then it gives very high proper. I mean, and then during engine operation, it gives actually 140. Yeah. Hello? Hello? Am I audible?
Yes, sir, it's audible.
Yeah.
Merin.
Sir,
it is okay.
Yeah, your question is over.
It is over means again this copper vessel any cryogenic treatment will get any benefit.
So you can ask Thomas sir. Thomas sir?
Cryogenic, no.
That's okay.
Only thing actually, I remember people have done some cryo rolling. See, the problem is actually whatever do you do it actually finally it has to be brazed. Brazed exactly that effect will be lost.
Okay, sir.
See, the only thing I cannot use a material in the cold work condition for a bracing. I mean, I can use it, but what the cold work effect will be nullified.
Okay, sir. Okay, sir. It's very nice. After a long time, very nice. This conference. Okay, sir. Very nice PPT. At least a student point of view, they can learn very basic things.
Yeah.
Okay, sir. Thank you very much, sir. Okay.
Students, any further questions? You may ask, please. Students.
I will come there. Don't worry. I'm not going to leave you.
Yes, sir. It's a very nice.
Your course will be over by June, July only. I will come there. Students, I'll catch you. Don't worry.
Sir, this is the undergraduate student. No, they are not understanding which one is a very important. Okay, that's why. But
because
nice,
technology and materials are very important.
Basic of,
every day I'm seeing.
Yes, sir. Yes, sir.
I'm not updating actually after left. Every day the things are happening.
Alloys, materials and are very minor.
Audio is gone.
Audio is muted.
Sir, Srikumar sir, after a long time you come in online. Okay, sir. Thank you very much.
Srikumar sir is my boss.
Yes, sir. Yes, sir. After a long time I meeting with online after a long time.
In fact, actually he was for
during
making
COVID
all these cryogenic materials. Actually, he was my guide. We
during
spent
COVID
a lot of time in industries actually to make because whenever material is not material, because developing a material is not a joke. When we make a material, actually we don't get properties initially, so we work.
Sir, we are always looking him, but during COVID period he is absent. That's why during COVID period we are not meeting him. Okay. Yeah. Thank you very much, sir. After a long time, we are observing you.
Merin, I have got a question to Merin.
Yes, sir. Tell me, sir.
Are the students present in the college or they were attending online?
Sir, actually, students are here in offline class. Right now. They're in the class.
Such a good presentation.
Sir, very nice
lot of questions.
Srikumar sir, tell me, sir.
No, it was such a good presentation. They should ask a lot of questions.
A lot of question is there. Lot of question is there, sir. Okay,
if they have got something, let them write it and give it to him.
I'm very happy because I don't know, Srikumar sir, my passion is actually teaching. I don't know. I don't know. I'm not. You can only judge me as good. I can talk well, or I can be a good teacher. But passing the information to students is I mean, I really enjoy taking classes for our younger engineers in ISRO, because I've been visiting ISRO. I mean, ISAC, PSSC for taking classes actually, and in fact they used to give me good grading about my teaching actually. I mean, I normally go deep and poke them to ask questions actually. I don't leave them because since it's online, I cannot do anything. I cannot see my students. Otherwise, I would have caught them. Like, it's not. I mean, they should ask questions. Then only things will be interesting actually, right?
Okay. Thank you, sir.
Yeah. Okay.
They're BTech level. They are not understanding what are this.
They will understand. They have to understand.
They understand. After going higher studies and this industry and all, they can understand, sir. Okay. Thank you very much. Thank you very much.
Sam.
Lot of thanks.
Yes, sir.
Yeah, you may continue, Sam.
So I would like to once again thank you for that amazing presentation, sir. So we would like to finish with by announcing all the winners of the events that had happened throughout the past few weeks. As we had said, there were many programs that were conducted throughout the week, like puzzle, we had a quiz, we had auctions, and there are various prize winners for that. I invite our the president of the Syndicate of Metallurgical Engineers, Mr. Rohit Narayanan, to read the names of the winners.
Thank you, Sam. Myself, Rohit Narayan, President of SME. Now, I'm here for the most awaited moment of announcing the prizes for NMD events. This year, we had 9 events, which went really well thanks to all of your participation. Without further ado, we'll get on with the prizes. Starting with the most prestigious JCJ Memorial Quiz. The first prize goes to Agila P. Suresh of Model Technical Higher Secondary School, Kalur. The second prize goes to Gobiga Santosh of Citadel Residential School. And the third prize goes to Aryendu Ji of Bharatiya Vidya Bhavan School, Chevayur, Calicut. Next, we will move on to this scramble event. The first prize goes to Naveen John, and the second prize goes to Tirtha Shantakumar. Now the prize for the treasure hunt. The first prize goes to Srinath Sudesh, and the second prize goes to Mohammed Swali. For Ludo, the first prize goes to Mohammed Hashim, and the second prize goes to Abhirami Ajay Kumar. Sorry for the delay. Okay. Yeah, we'll continue. Now, for the IPL auction, the first prize goes to. Okay, sorry for the inconvenience. We're having some technical problems. We'll be back in 1 minute. Okay, so the prize for the IPL auction, the first prize goes to Team KKR. The participants are Paul Jose, Arjun Tafim, and Libin. And the second prize goes to Team Mumbai Indians, consisting of Andrew Dixon, Anil Thomas, Alan J. James, and MK Narendra Prasad. For PUBG, the first prize goes to TFT Esports, led by Kavya Prem Kumar. And the second prize goes to LSD Esports, led by Subin Ninan. For photography, the first prize goes to Haridev, and the second prize goes to Roshan M. Premsar. And for poster designing, the first prize goes to Ajina Shaji, and the second prize goes to James Roy. For the reels, we had 2 categories. For reels, we have 2 categories. For the dialogue category, the first prize goes to Ashwati NS, and the second prize goes to Neha Pia. And for the dance category, the first prize goes to Sandra S, and the second prize goes to Elna Shaji. No, that's all. Congratulations to all the winners. So thank you for your valuable participation, and we'll meet again next year.
Thank you, Rohit Narayanan, for that. Congratulating all the winners. The prizes and the certificates will be given to all people, all the participants in time. They will be personally contacted. The link for the certificate for the webinar is put in the chat. Please do fill that form out. We thank you all, each and every person here. including all the students, teachers, the professors, and everybody who has taken their time today to give us, to be part with us in the celebration of National Metallurgist Day. We invite you all again to be a part of it next year. We hope that you will show your continued support and gratitude to all of us. So I would like to thank all of you, and this is Sam Jr. signing out.
I request everyone to fill the form. Please find the attachment. Please fill the form.